All right, hello. We're going to get started on chapter 13 now. So what we're going to get into here now are vector valued functions. And so previously you're probably used to scalar valued functions. You plug in a scalar and you get a scalar value back out of it. Now what's going to happen with these is we're going to plug in, well, you can really plug in vectors or scalars, but we're going to, I think, mostly plug in scalars, and the output is going to be some sort of vectors that come along with what we're doing. All right, so without further hesitation, let's get started on 13.1, curves in space and their tangents. Sorry, that's a little wonky, but let's go ahead and look at this. So if we have some sort of curve going off in three-dimensional space, you're going to essentially just make this a parameterized function almost. You're going to look and divide this up into its components, and then there's going to be a function for each of the three components, x, y, and z. And then all the points that these functions make together for their corresponding values of t will be points on the curve. And so that's what you'll have here is, your x, y, and z will be individual little functions like that. And they make up the curve in the space that we call the particle's path. So a lot of this is thinking along the lines of a particle moving along this path. And at different times t, which doesn't necessarily have to be time, but that's why we use that t, it will be at different positions along that curve. The equations in interval, they parameterize the curve. And then the vector here, right here, here's our vector function, r of t, which you would write with a vector symbol over top of it, is equal to, and you can see this here, it's the vector that stretches from the origin, you see it over here in the picture, from the origin up to point P, where point P is some point on the line or on the curve there, and that vector is labeled in the picture there as r, and it's red. And so your parameterizations, you have your function of time for the I component, function of time for the j component, and function of time for the k component. And that's the particle's position vector at a time t. All right, so that's our basic idea here for what our vector function is. Here are some examples of some different vector functions where you can see some kind of craziness shapes you get going here with sine of 3t times cosine of t is the I component, sine of 3t times sine of t is the j component, and then the k component is just t. And then you can see some other ones here and see what kind of crazy shapes you get with these computer-generated ones based off these position vectors. All right, so take a look at those. Here's another one. This is a graph of the vector function. This is essentially like a unit helix here instead of a unit circle. If you project this down, you can see that this, if we only looked in the xy plane, it would just be this equals cosine t plus sine t. That would be the unit circle. But we also are now moving in the k direction at a rate of t. And so it kind of spreads us out, so you spiral up now instead of just going around the circle like you would if you were in just the xy plane. And the interesting thing is, of course, you start here at t equals 0 and you make one full revolution at 2 pi. So it is like a unit helix. This helix from the center of it all the way out would have that radius of 1. Okay, so there is an example of one for you there, getting a helix going. Here are some different helixes. If you change the value of the coefficient on the k term here, this is with just t, this is with 0.3t, and this is just, well, actually, no, we're not changing that one there. Here we're changing the sine and cosines angular frequencies there. So there we go. We've got some differences that you can go in and change and make and get different helices there. Okay. Here we can go ahead and actually define a limit for our vector functions. And if we have a vector function here, and essentially we can say that it can have a limit L as it approaches t, or as t naught approaches t, we can have a limit of the vector function there at that point. So this is very similar to the limit definition that we had before. It's just now being applied to a limit vector L. And so when you take the limit of a vector function, the limit is now a vector that it goes to. And then, of course, there has to be an epsilon greater than 0. Well, for every epsilon greater than 0, there has to be a corresponding delta greater than 0, such that that is true. So hopefully you remember that that's back from Calculus 1 when you first start doing limits. If you don't remember that, go ahead and look back and see the corresponding epsilons and deltas there. Here is an example of actually taking the limit. So here we're given a vector function, and we're asked to take the limit as it goes to pi over 4. There's nothing too complicated here. You can actually distribute this limit onto each component and take the limit of each one of the functions individually. And so the limit of cosine of t as t goes to pi over 4 is just that. And so it doesn't go to 0. You can basically just plug it in. And the same thing for sine of t. The limit is t goes to pi over 4. And then the limit of t is t goes to pi over 4 is just pi over 4. So pretty straightforward and should pretty much go right along with what you already know about taking limits. Just apply it to each component. Here we have a definition for a continuous vector or continuous at a point. So a vector function RT is continuous at a point t equals t naught in its domain if that limit equals r of t naught. So if the limit as t goes to t naught of the vector function equals the actual value at that point, then it's continuous. So in other words, there's not some break. We have some spiral going along, and this is where t naught is, and the limit, as you push in from there is the same as the actual value at that point. It's not like something like this where you come along and then there's a break there, and maybe there's another value up here for that exact moment, in which case the limit, right, the limit would be, say coming from the origin would be this vector, but the actual value at that point would be this vector. It would be broken, and it's not continuous. Whereas here, the limit is that value, and the actual value at that value is that value. Okay? And then if the function is the function is just plain old continuous if it's continuous at every point in its domain. All right. Next, let's look at this example here. It says all the space curves shown in figure 12.2 and 12.4 are continuous because their component functions are continuous at every value of t in negative infinity to positive infinity. And then B, the function g of t equals cosine of t plus sine t plus what we have here is the greatest integer function here, and it's going to be discontinuous at every integer where the greatest integer is taken, because that is actually a discontinuous function because it's causing you to round. So you're going to get stepping like that, where it's going to be discontinuous right every time you're hitting an integer, you're hitting an integer, you're hitting an integer, and you're going to get these steps that are going to occur because of it. All right. Excuse me, let's take a look here. This is just some, again, some vector functions here where you have position vector r of t, and then you have some time step delta t, you're stepping forward, and you have a function r of delta t in the first picture. That's what they're showing there. As delta t goes to 0, the point Q approaches point P. So we're going to, as we take that limit, we're going to push that point Q. You're going to push that point Q over to approach P like that along the curve C. In the limit, the vector PQ over delta t becomes the tangent vector r of t. So as we take that limit, we end up finding a vector that is tangent to our curve there. So that should again sound very familiar to our previous things where we did derivatives and found lines that were tangent to our curves. So let's go for a definition here. The vector function r of t equals f of ti plus g of tj plus h of tk has a derivative, in other words, is differentiable at t if f, g, and h have derivatives at t. The derivative is the vector function. So what we're doing here is we're essentially saying the derivative r prime of t, or dr dt, and again, remember, that's a vector. That's a vector function. Those are vector functions, okay? Is equal to this limit. So this limit should look very familiar to you, right? F of x plus h, right? The f of x plus h minus f of x all over h thing as the limit as h goes to 0. So it's just an extension of that. And then what you're essentially going to be able to do is just take the derivative of each individual term with respect to t. So dr dt is just the individual derivatives of each component there, okay? So a vector function R is differentiable if it is differentiable at every point in its domain. Then it's just differentiable. The curve traced by R is smooth if dr dt is continuous and never 0. Okay? So let's take a look ahead here. So here what we have is a piecewise smooth curve made up of 5 smooth curves, but they're connected together. And where they're connected together, though, is not smooth. So this is nice and smooth, but not right here. So we can take vectors, we can take derivatives here, but not right there. So right where it's not, where they're connected, where it's not smooth, we have some troubles there. So let's do another definitions here. If R is the position vector of a particle moving along a smooth curve in space, then V is called the velocity vector, is the rate of change, is the derivative dr dt, and we call that the particle's velocity vector, and it is tangent to the curve at any time t. The direction of V is the direction of motion, so as you increase t, V will point the direction toward where you would be moving along the curve. So if you are here and you have this curve here and you've got a velocity vector like that, then you know that you are actually moving in this direction as t goes up. You wouldn't be moving back in the opposite direction, okay? So it points you out the direction that it's moving at that moment, which is tangent to the curve. The magnitude of V is the particle's speed, all right? So that's where we're just basically getting rid of any directional information. And the derivative, A, equals dv dt. So in other words, a second derivative of our dr, of our radius function here, our vector function, when it exists, is the particle's acceleration vector. So we can get a vector function from that. And so here's a breakdown of that. The velocity vector is the derivative dr dt. The speed is the magnitude of that dr dt, the magnitude of that velocity. The acceleration is the first derivative of the velocity or the second derivative of the position function. And the unit vector v over its own magnitude of v is the direction of motion at time t. Okay, so let's take a... All right, so I had made a mistake in this one, so I'm splicing in a correction here for this problem. So I'm just going to kind of walk you through it. Here we're supposed to find the velocity, speed, and acceleration of a particle in space whose motion is given by that vector function there. R of t equals 2 cosine t in the I direction plus 2 sine t in the j direction plus 5 cosine 2t in the k direction. All right. So to find the velocity function, we just need to take the derivative of the position function. So we do that by taking the derivative of each component individually. So we get the derivative of 2 cosine t. It gives us the I component of the velocity function. So derivative of cosine is negative sine. We can do the derivative of the j component here to get the j component of the velocity right there. So the derivative of sine is cosine, just carry the constant along. And then here we do the derivative of the k component where we have to do chain rule because we have that 2t inside the cosine. So it becomes essentially the derivative of the cosine, which is the sine part, times the derivative of that 2t, so it's times 2, which means that 5 becomes that 10. And or derivative of cosine negative sine, so it's got that negative there. And so that gives us our velocity function right there, just the derivative of the individual components of the position function. Next we have to find the speed, In order to do that, you simply take the magnitude of the velocity function. So usually, if you're talking about speed, a lot of times it's written as the velocity v, symbol, but without the vector symbol above it. So it's just the scalar version of it. So it's the magnitude of the velocity vector function, and you get that by squaring each component, right? Adding them up, squaring each one of them, adding them up, and taking that square root. And then that gives us our speed as a function of time there. And of course here we have 4 sine squared plus cosine squared. You can factor out that 4, which gives you sine squared plus cosine squared, which is 1, and leaves us with 4 times 1, or just a 4 there. So that's how that step happened. Last, we want to find the acceleration function here. And to do that, you simply do the derivative of the velocity function. So we're going to take the derivative of this one up here now. And again, do it component by component. So the derivative of the I component will give us the I component of the acceleration. The derivative of the j component will give us the j component of the acceleration. The derivative of the k component will give us the k component of the acceleration. So you just go through and do those each individually. What I also wanted to point out here was if you look at this result here, and you look at this initial result here, you can see that they're different just by a negative sign and a constant vector being multiplied into there. You see that we've got, negative cosine, and this was just cosine, negative sine, and we had sine. Here we have this extra constant here, but again, it's a negative cosine and a cosine. And so anytime you're taking derivatives of a position that is based on sines and cosines in a way like what is done here, you essentially get that the second derivative of it, which is our acceleration function, is just the first derivative times a negative times what is essentially the angular frequency there squared, right? So this is, what is this? This was 5, it became 20, so it's times 4, and that's that 2 squared right there. Okay? So that's it for this, and I'll slice this in and continue on with the rest of it. Okay, here are some differentiation rules for vector functions, and again, most of these should look pretty familiar. They're pretty much just extensions from the similar situations when you're dealing with scalar valued functions. So here we can let u and v be differentiable vector functions of t. C is a constant vector. The lowercase c is any scalar, and f any differentiable scalar function. So first, constant function rule, the derivative of a constant vector is 0. Constant vectors aren't changing, and so again, well, it's the 0 vector, I should say, but it's still analogous to the derivative of a constant scalar is the 0 scalar. Derivative of the constant vector is the 0 vector. Scalar multiple rules. Again, you can essentially move a scalar out in front, so you could have c times d dt of u of t, like that. So you can essentially move them right out in front. You can move it out in front. And you can also get the same thing from doing the product rule for that, where that derivative of that constant will become 0, and so that term will go away. But you can do that. Here with a vector function, you can notice this is essentially the product rule, where it's the derivative of the scalar function times the vector function plus the scalar function times the derivative of the vector function. So again, still derivative of the first times the second plus the first times the derivative of the second. There's a summation rule where we can just distribute this through and do the derivative of each individual vector function like that. Next, difference rule, same thing, distribute it through across the subtraction. The dot product rule, notice again, this is just product rule. Derivative of the first dotted with the second plus the first dotted with the derivative of the second. So we're getting that same thing, and the same thing here with the cross product rule. Derivative of the first crossed with the second plus the first crossed with the derivative of the second. And then the last thing is that you do have to chain rule these. If you're doing the derivative of this and you have to do that, you have to chain rule it. So chain rule works here as well. Okay, so let's take a look here now at this vector function. So if you have a particle that's moving around on the surface of a sphere and never leaving it, what you would find is that the velocity vector, dr dt, is always at every point going to be perpendicular to the position vector. So if this is our position vector here, the velocity vector is always going to be perpendicular to it, right? No matter where we look. If we look up over here, this is our position vector, and then the velocity vector would be like that, and it would still be at a right angle on there. I didn't do a right angle sign, but it would still be on a right angle there between them. And so if we assumed, for example, that Earth was a perfect sphere, then everywhere you've ever walked or driven around on Earth, your position from the center of Earth, your position vector, has always been perpendicular to your velocity vector throughout this entire thing. And that should make sense. No matter where you're going on there, the position vector is always pointed out radially to the surface, and then you're always moving tangent to the surface. Therefore, it's always at a right angle, and therefore r dot dr dt is always going to be 0. Okay? And so that just leads us to this. If r is a differentiable vector function of t of constant length, in other words, it's always pointing out to the surface of a sphere, then r dot dr dt is going to equal 0. All right, I think that's it. Yep, the next is the next section, so we're going to go ahead and stop there. I hope that made some sense to you, and I will see you next time.